Okay, so here we have an initial value problem. We are going to solve it using a Laplace transform. So our first step is we're going to take the Laplace transform of both sides. Just to help us prepare for that, remember that the Laplace transform of y, we're going to write as big Y, just to make it easier to follow things around, and so we don't get lost in the notation. The Laplace transform of y prime is equal to s times the Laplace transform of y minus the value of y at 0. And if we look at our table, the Laplace transform of 1 is equal to 1 over s. Okay. All right, so we're taking the Laplace transform of the left side, and we get y plus 3 times s times capital Y minus little y at 0. So minus 2. On the right-hand side, we have the Laplace transform of 1, so we get 1 over s. Next, we're going to solve for y, which again is the Laplace transform of our solution. Okay. All right, so we see y in 2 places. We're going to start by distributing. So we have y plus 3sy. Oops, that's hard to read. Let's try that again. Y plus 3sy minus 6 equals 1 over s. Okay, so everything that doesn't have y as a factor, I'm going to move to the other side. So we have y plus 3sy equals 1 over s plus 6. If we wish to, on the right-hand side, we can combine everything into a single term. So that's 1 over s plus 6s over s, or 6s plus 1 over s. All right, our goal was to get y all on its own. So we see it in 2 spots on the left. It's a factor of both of these terms, so I'm just going to factor it out. Okay. All righty. And now we can divide through by 1 plus 3s. Okay, so when we look at this term doesn't show up in our sheet, but what we can do is use the partial fraction decomposition to break it up into smaller pieces that we do recognize on our list. So one just tiny little thing that I think would be helpful here is that because we see this one of these terms has a coefficient that's not equal to 1, I'm just going to pull out that 3 in front. Let me just write this out. So just because we see this 3 here, let's pull it out in front. So that gives us 3 times s plus a third times s. Okay. All right. And now we are ready to go. We're going to break this up into a couple of pieces. So we have okay, so because the pieces that we're going to be taking inverse Laplace transforms sort of best have coefficients of 1, I think I'm going to just rewrite this a little bit before I break it up, so that it looks like I'm going to bring this 3 up into the numerator. So 2s plus 1/3 over s plus 1/3 times s. Okay. That way we feel pretty good because each of these pieces just has a coefficient of 1 in front of it. Okay. Now we can use the partial fraction decomposition, right? So we're finding our partial fraction decomposition. We can use either the cover-up method if we like, or we can clear out the fractions, either plug in values of s or compare the coefficients. Because we have non-repeated linear terms, I'm just going to use the cover-up method here. So A, we're going to get by evaluating this expression when s equals -1/3. We're going to cover up this s plus a third piece, and then we're going to be evaluating 2s plus a third over s. So this gives us 2 times -1/3 plus a third over -1/3. -2/3 plus 1/3 gives us -1/3. Divided by -1/3 gives us 1. Next, we're going to look at B. So to find B, we are going to be looking when s equals 0. We're going to cover up this s. And so we have 2 times s plus a third over s plus a third. And so this gives us 1/3 over 1/3 or 1. Okay, and so this simplifies to a over s plus a third plus b over s. Okay, so it is time to, so we solve for y, maybe 3 here, find partial fraction decomposition if we need to. And then step 4 is we're going to find the inverse Laplace transform. So we're going to take the inverse Laplace transform here of y of s, which is equal to 1 over s plus a third. Oops, that's supposed to be a 1 on top, plus 1 over s. And so that tells us that our solution y of t is equal to e to the -1/3 t plus 1. Because this first term here is 1 over s minus -1/3. And so we use that exponential rule with our a equal to -1/3. Okay, all right, and we did it. So when we look at first order cases like this, maybe this feels like a lot of work when we could just, use integrating factors. But this is good practice for when we look at second order d's, and then we will soon look at more complicated functions on the right hand side, where this becomes like a better and better tool. So this is just sort of the training wheels version, and we will get to some like actually good applications soon.